Hello, I'm Nick Solomey, and this is my NIAC Phase 3. It's a CubeSat spaceflight test of a neutrino detector capable of operating in space. Solar neutrinos come from the fusion core inside our sun. We detected solar neutrinos here on Earth at the small number in various experiments. But this project started off as a NIAC Phase 1, which was a simulation-based study of the concept. And it developed into a NIAC Phase 2 for laboratory detector R&D tests for a space-based neutrino detector. This current NIAC Phase 3 is the construction of a CubeSat for polar low Earth orbit to study backgrounds of the double pulsing technique for identifying solar neutrinos. And our hope is to launch this test detector in a 3U CubeSat by the fall of 2024. Eventually, the hope is a future mission called the Neutrino Solar Orbiting Lab would go very close to the sun after the development of this detector. And we've done some studies of budgeting of that in our Phase 2. This project is a scientific cooperation between my group here at Wichita State University in physics, along with Wichita State University Aerospace Engineering, NASA's Marshall Space Flight Center in Huntsville, Alabama, South Dakota State University, the Jet Propulsion Lab in Pasadena, California, and the University of Minnesota. We've had R&D funding to support this. The idea for this project actually started in 2015, and a small NASA EPSCoR partnership development grant between myself and Marshall Space Flight Center allowed us to communicate and visit and exchange ideas. We also got a Watkins Private Foundation Fellowship to support some of my effort, as well as a cooperation across university disciplines to get aerospace engineering interested in our project. This led to myself having, in the summer of 2017, a NASA Summer Fellowship. And we submitted in 2017, we submitted a NASA NIAC Phase 1 proposal, which we received. We had some funding in a gap from Marshall Space Flight Center Cooperation Grant in 2019. And then we started in the fall of 2019, a NIAC Phase 2 laboratory test for 2 years. This was then followed by a NASA NIAC Phase 3 grant, which was started in October 1st of 2021. And we've also had some equipment funds from the Simons Foundation, which is part of Wichita State University funding. The technique of our detector to detect solar neutrinos is a little different than these large detectors here on Earth that are buried deep underground. If we're going to detect a neutrino in space close to the sun, we need another technique other than just being able to shield our detector from lots of space radiation. And our technique goes back to the 1950s technique developed by Cohen and Reines to first detect and observe the neutrinos. So we actually didn't invent this, but we want to use it in space. If we have a large amount of gallium, which has a high cross-section for neutrino interactions. The gallium that we've chosen is a crystal called a GAG crystal, gallium, aluminum, gadolinium, garnet. It has 20% gadolinium and has this fast light yield. If a solar neutrino comes in, it can interact off the gallium. It produces a conversion electron, shown here as a red line, and we can see that. And it then has a excited state germanium nuclei produced, which has a microsecond half-life, well, 2.5 microsecond half-life. And it then decays with a very well-known gamma ray emission. Well, actually, 2 different gamma rays are possible, 2 different energies, that is. And our detector, shown here in this little cube that's being illuminated by UV light, and you can see the green light glowing, are 4 GAG crystals. And each one of those is being read out by 4 silicon PMs. And what we're doing is reading those out by silicon PMs. We're going to encase this inside a veto ray, an active veto ray made out of plastic scintillator. And then we do have to encase it in some shielding just to cut down on the space X-rays. There's a lot of low energy X-rays in space. And what we're going to do is look for this double delayed coincidence timing pulse. And eventually, once this construction is complete, the hope is to secure a launch assignment and a couple years of funding for operations. We have already secured a NASA SCANS, that's the Space Communication and Networks Near Earth Network Communication Grant for $235,000. And so our hope is that sometime in this coming year or last year of this NIAC Phase 3, we'll have secured the launch assignment after demonstrating we're ready to go. So if we can operate a neutrino detector in space, what new science can be done? On Earth, a few hundred solar neutrinos have been detected from the sun's core. These, by going closer to the sun, such as the 1/r² dependence, would let us see much higher flux of solar neutrinos. Just getting out to Venus is 2 times more solar neutrinos than here on Earth. If we could get to where Solar Probe Plus quite often goes, 7 solar radii, would be 1,000 times more neutrinos. And we could have this double pulsing technique and a much smaller detector. Obviously, a 1 kilogram active detector would be equal to 1,000 kilograms when you get the 7 solar radii. And hopefully, someday we'll be able to go to 3 solar radii, where NASA wants to be able to go someday to study the sun even more. And that would be 10,000 times more solar neutrinos. But there's other ways in which we could use this detector. Dark matter, or the searches for dark matter on Earth, are being currently limited by the solar neutrino background. But at the current location, say, of the Voyager probe, it's actually the solar neutrino background would be 20,000 times less. So it would be an advantage if you have a detector searching for dark matter to go away from the sun. And there's a third possible place you could look for enhanced intensity of neutrinos, and that is the gravitational neutrino focus of the sun. You could concentrate 10 to the 9, 10 to the 12 times neutrinos, and if you were to look at the second brightest neutrino source in the sky, the galactic core, with over 10 to the 26 stars in it, and the sun is concentrating those neutrinos, because the neutrino has a slight mass, although albeit small, you'd be able to look at the highly enhanced neutrinos from all the stars that are currently in the galactic core. So what is the work that's currently being done? Our NIAC Phase 3 has been in progress now for almost a year, coming up on October 1st. And we currently have the work divided as follows. We have 4 GAG crystals, which you saw a picture of. Each will be read out by 4 of the silicon PMs. And this is already constructed and testing. I'll show you some of the results next. And this part of the project is being led by Wichita State University Physics. We have a veto array that these GAG crystals will be surrounded by, and that's Marshall Space Flight Center. And I'll show you results from that as well. We have shielding and mounting. We want to shield this detector a little bit and mount it into the CubeSat. And that's being led by Wichita State University Physics as well as JPL. The CubeSat has been ordered for $239,000 from NanoAvionics. We are working on dedicated flight electronics, a high voltage card, a signal receiving card, and a logic card. That's all under construction at Marshall Space Flight Center, and those cards actually physically exist for their version 1. And we have payload and flight controls that'll be undertaken by Wichita State University Physics and the Wichita State University Aerospace Engineering team. We have flight detector simulations, which are being done at South Dakota State University, as well as graduate students here at Wichita State. We have thermal and power, which is being worked on by NanoAvionics as well as JPL on the team. And communications with our S-band was being worked on by Wichita State University Electrical Engineering, NanoAvionics, and the NASA Near Earth Network. The test detector will occupy 1/3 of a 3U CubeSat. Here's a sketch of our 3U CubeSat, and in blue down there is the outer shielding, and you can see that's being mounted inside the frame of the CubeSat. And the detector will then sit next to the 3 Marshall Space Flight Center dedicated electronics card, and then the rest of the space will be occupied by flight cards, flight computer, payload computer, power cards, avionics cards to help orient it, all being part of the NanoAvionics 3U CubeSat order. This will be fixed in place with our detectors in a sliding key mechanism. And we should then be, after final assembly, with an S-band antenna on the bottom, we should be ready to undergo vibration tests and eventually launch. Some results have already been done. Lab testing of our GAG crystal occurred here at Wichita State University. We've been using beta decay sources from strontium and the secondary yttrium decay because there's a similarity between the conversion electron that would be produced in solar neutrino interactions and these beta decays in our detector. So we're looking at the energy tagging to make sure we know how to identify which ones are electrons and the length of the tracks and any timing restrictions it places. We've also been looking at gamma ray sources, energy resolution, linearity, signal shape, because the secondary double delayed coincidence is a well-known gamma energy, and we could use gamma sources to emulate that. Here's a depiction of the sodium, but in this plot here, you could see a depiction of cobalt-57, and on the right, you see barium-133 with 4 different gamma rays. And we're seeing exceptionally good energy resolution because the GAG crystal is known to have almost down to 4% energy resolution. Now, we won't see that because our beta decay conversion electrons are broader signal, and of course, other limitations. But here's some linearity plots of our 4 crystals. One has slightly higher gain intentionally than the other 3. And you can see the linearity where we're going down to 10% energy resolution when we got out there to 700 keV. So the 4% energy resolution is expected at 1 MeV. And we're projecting almost that when we get the projection of our energy resolution. So we've been testing our GAG crystal. We've also been studying with simulations our double delayed coincidence. Again, the neutrino comes in, produces that conversion electron, which is depicted as red. And down here in the pulse height plot, we show you what some of the simulations say it would look like. And then our gallium is converted into an excited state germanium 66% of the time. And it then decays with a well-known half-life of 2.5 or 5 microseconds, depending upon which particular mode we're looking at. And we could then see a double delayed gamma pulse. And we're seeing in these simulations, and eventually, hopefully in our flight test, the goal is to measure the real backgrounds from galactic cosmic rays and galactic gamma rays that would emulate this. And so that'll allow us to determine how efficient or how many events we'll really have when we get close to the sun, and how many background events we have to learn to live with. The scintillator Vito detector is being built at NASA Marshall Space Flight Center. It's going to surround the GAG crystal. And here's a picture of the scintillator itself. And there's the top cover you see next to it. And just to get a sense of the scale of a size, that's just a normal size coffee cup. And Marshall Space Flight Center has been testing this efficiency of this detector from all different sides and different angles using an americium-241 source. And we're seeing, the performance we really need to do that. All of this will be encased inside the shielding array. So construction of our components, our electronics boards have prototypes underway. Our main detector, the GAG detector, is built and tested. The Vito ray is under studies. And our hope is that we'll have a CubeSat launch in somewhere in 2024, either with a SpaceX or a Rocket Lab rideshare. Our 3U CubeSat is about 8 kilograms, a little less actually. And our hope is to go into a polar low Earth orbit so that when we're over the poles, when we're not underneath the radiation belts, that we'll be able to see the real cosmic ray and gamma ray spectrums of deep space. And it's only 12 minutes every orbit out of the 92-minute orbits. And that's when we'll be taking data. And the rest of the time we'll be sending data down, such as with our S-band antenna. The ride, if we got onto a rocket lab, would only be 4.5 Gs. And if we got up to a SpaceX, we would expect to have to survive 8 Gs. And a launch, if you go directly to the launch providers, $180,000 for the launch. And we need to secure 2 years of operations. And we already have a communications grant from the Space Communication and Networking. So our aim is the launch in late summer of or fall of 2024. And we will be a little bit delayed because our NIAC Phase 3 should end in October of 2023, but some components are delayed, but we expect that would easily still make our hope launch date of summer or fall of 2024. So thank you very much.